In this presentation, I'm going to go over Bruce BdM's expected outcome of conflict that he uses. This is basically his expected utility calculations for conflict, whether that be a war between nations or a conflict between different powerful people in a decision-making process. To put this in context, the expected utility model of conflict I'm about to go into kind of says, okay, what do we expect to happen with when people or actors or players go into conflict with one another? Now, this can be a war, or it can be a contest or a conflict within the decision-making process. BdM models all of this in an extensive form interaction game, of which the crisis subgame that I covered in a previous video is what you're seeing here. And that crisis subgame occurs when one player makes a demand to the other one, and the other one not only doesn't accept it, but issues a counter demand. When we have competing demands on the table, it's either we're going to fight or we're going to negotiate over this, or one of us is going to roll over, right? And so that's basically the outcomes we have here. The crisis subgame ends with 5 different outcomes, right? And the capitulate A, capitulate B, player A capitulates, gives up to player B, or that's obvious, right? And when that happens, the other guy, if B capitulates, A's, gives in to A's demand, right? So that outcome's pretty clear cut, deterministic. There might be some costs associated with it, but still. The question is, what happens when you go to war or when you negotiate? And basically, the war is what we're about to look at, right? What do we expect to occur when these two dogs go at it, right? The two big dogs fight, or maybe it's a big dog and a little dog. That's the point. We need a prediction of it. And the idea here that runs through this is that negotiations will be basically, if you're negotiating as an alternative to war or conflict, the negotiation will reflect what would have happened if you went to conflict. And so, just minus the costs of fighting, right? And so the thing is, the expectation of what would happen if you went into conflict drives 3 out of 5 outcomes here. It drives negotiate, war B, and war A. That's why this is such an important thing to look at. Now, we're not going to look at the costs associated with war in this. We're just going to look at what the prediction is about what outcome will occur if conflict occurs. Okay, so how do we calculate the expected outcome of conflict? And so let's suppose we got 2 players, A and B, right? And remember, in the forecasting model, for each player, we've already calculated their influence, their salience, and their ideal position, right? So influence 100 is, the most influential person gets 100. There can be more than one with the same, that if you've got 2 very influential people about the same, you can have 200s in there, okay? But then everyone else is less than 100 based on, relationship. How much influence do they have over one another in comparison to one another? Then we have salience, how much do they care about the issue? And then there's the position, and so, which is usually P, right? So we have I, S, and P, right? The intuition here is conflict is going to be a function of the player's power, right? Which has previously been defined as influence times salience. How much influence do they have, and how much do they care about the issue? But we're also bringing in the difference between positions between player A and B, right? Because this is what's being fought over, right? A has made a demand for its position, and it's assumed that it just demands its favorite position. B then makes a counter demand, its favorite position. And the difference between these two things is what they're fighting over. I say it's the stakes, right? And so, clearly, if there's a big difference, you're fighting over a big difference in policy. If there's a little difference between A and B's position, meh, right? And kind of the idea is you're not going to fight. The stakes aren't high. You're not going to fight as hard. And so all of these 3 things come together to measure in some way the effort that we expect people will be willing and able to put into the fight. Important thing here, we aren't just looking at capabilities. We are factoring in how much they care about the issue and what's at stake, right? So we're going beyond just a capabilities estimate into intentions, if you will. Okay, so what you do is you to figure this out, you just multiply the influence times the salience times the difference in positions between the two players, right? All of these things are, easy to do, really. And then you divide by the sum of both, right? And very straightforward. Now, I'm going to make it look ugly, right? Here it is in math language. The probability A prevails over B, otherwise known as probability A over B, is equal to, and what we got going on here is just on the top, we have influence of A times salience of A times the absolute value of the difference between position A, A's position, and B's position, right? And those are just the three things I just said in words. Here it is in math notation. And that equation looks ugly, but it's really, this is the same as this. And then this is B's calculation, right? We do the same thing for B. B's influence times salience, difference between B and A's position, right? Which is basically the same things up there. And, really, it's not that much going on here. We have one thing that we calculate for each player, and then we put it in, we put them in a fraction, right? So not a really big deal. So what do we get? Okay. By the way, once we calculate A's probability, B's probability, we just, say, well, 1 minus, once we figure out the probability A wins, mathematically, the probability that B wins is just 1 minus the probability of A, what we just calculated, right? So we have 1 minus probability of A over B. And then to figure out the outcome, here's the outcome, right? To figure this out, we're going to look at, we've got this. We're going to say, all right, there's two sides to this. We have the probability that A is going to win, right? The thing we calculated first. Now we're going to multiply that times, now here P means position, right? Position of A, right? So with that just basically says, whatever A's favorite position is with probability, the probability of A over B, it's going to get it. Then we also have the probability B wins, right? 1 minus probability of A over B. And we multiply that times B's position, right? And together we get an estimate of where between those two positions they're going to be, right? And it's going to be influenced by this probability calculation. Let's take a look at an example of this. Okay, for our example here, we have two players, A and B, right? And let's suppose that these are the numbers we have, right? That for A, the influence is 100, the salience is 50, and the position is 80, right? And so and this has all been calculated. This is what you do when you start the model. You identify all the players involved, and then you make these estimates, or you have experts do it for you. Now note, A is one of, if not the, is got maximal influence, right? And in fact, if A was more powerful than B, the way you calculate it is you would make A 100 and then B would be somewhere less than that. And it's been calculated, A is more influential and B's got about half as much influence, right? Because when we go down to B, we see B has a 50. For salience, A is not so into this, right? A is not really, A's got a 50. And so A is kind of in between. We care about it, but we'd also like to make a deal with people in life. And so it's not, we'll trade on this issue, basically. Whereas B is very salient. B's got a 95. This is very important to it. Finally, for position, I don't know what it means. It's just hypothetical. A is at an 80, B is at a 40. With those numbers, though, we can calculate everything that we talked about in the previous slide, right? So we start off by calculating for A. We have, remember, influence times salience times the difference in position. Influence for A is 100, salience is 50, and A's position is 80, B's position is 40, so 80 minus 40, absolute value, by the way, that's 40. And I'm going to leave the arithmetic out of it. you're going to end up with 200,000, right? So that, what, I don't know, it's just a number. If we keep going here, we're going to see, all right, we do the same thing for B, and you can see it's same thing. We get influence times salience times the difference. We get 190. Okay, so we've calculated for both of them the product here of these three things. Now we calculate, we could do this, right? And we go, all right, what is that? Well, this is that. It's 200,000. So we put 200,000 here. And the bottom is the sum of both. So we sum both of these up. 200,000 plus 190 is 390. Right, really don't need a computer for this. Well, I like a calculator for this, right? We come up with, if we round, 0.51, right? So we have a prediction here of a 51% chance that A will win, a conflict, that A will prevail and get its position. So what do we do with that? Well, by the way, we're not done. We calculate, if there's a 51% chance A will win, guess what? There's a 49%. It's not rocket science, folks. 1 minus 0.51, right? If one guy's got a 51% chance of winning, the other person's got a 49% chance, right? I mean, that makes perfect sense. So those are our percentages. Now we got to calculate the outcome, right? Remember, the outcome, we multiply the probability. We multiply the probability of A over B, right? That's there, times the position of A, which was 80, right? And so we have 0.51 times 80. That's the first part. Then here, 1 minus the probability, which we calculated up here, times B's position, which of course was 40. And so we have that there. So we just, 0.51 times 80 plus 0.49 times 40, we get 60.4. This is the prediction of the outcome, that if these guys fight it out, they're going to come up with something that, do we need to round here? Probably not. We should probably just say 60. Or we shouldn't have the decimal point, right? 60.4, I don't know. But it's a 60, right? We're going to come out about halfway between their two positions, because even though A is twice as influential as B, A does not care as much, right? There's less salience. B is very salient. So it's basically an even match between the two, right? And I think that tells you something about what goes on here, that we're doing more than just looking at who is the most powerful. We are saying, what effort will they put into this, and how is that likely to affect the outcome? But hey, what if there are N players, more than 2 players involved, as often there are? Well, conflict may not be restricted to just them fighting it out. Other people will probably join in, and they will certainly, A and B will try to get them on their side. So how do we calculate the expected outcome of a conflict with more than 2 players? So the intuition here is that in a conflict between A and B, other players will ally with A or B based on their policy position, right? And so somebody who prefers A's position over B is going to help A out. Someone who prefers B's position over A is going to help B out. And I'm going to talk about coalitions and use A plus and B plus to identify a coalition, right? So in god-awful math term, coalition A plus includes all players I, such that the difference between I's position and B's position, the absolute value, because it might be higher or lower on the scale, we don't care. All we care about is the distance between the two, right? That absolute value, right, is bigger, right? The difference in position between I and B is bigger than the difference between the position of I minus position of A, absolute value. So basically, if the difference in my position versus B is greater than the difference in my position versus A, I prefer A's position. They're closer to mine, right? So I'm going to be part of coalition A plus. Team A plus, baby. And do the same calculation for B, right? I'm not going to go into that. We've already complicated this enough. Then what we've got to do is do calculations similar to what we did before. And for each coalition member, we're going to multiply that player's influence times the salience. And now the difference in differences between positions, because now a coalition partner isn't fighting, right, for their favorite position. If you're on team A plus, right, if you're on A's side, you're fighting to get A's position. So you're not going to get your favorite position out of this, but you're going to get something better than what would occur if B won. So the question is, what's the difference in these differences, right? How much of a gain is at stake? So we have to calculate the stakes just a little bit differently, although it's not too crazy. Let's take a look at what that looks like. All right, well, maybe it is getting crazy. For each coalition, A plus, right? And the math here is we're going to sum up for each I in coalition A plus, which you've already calculated, figured out who's on what side by figuring who's closer to who. For each player in the coalition, you multiply that player I's influence times salience times I minus B minus I minus PA, right? The position of I minus position of B, which is the difference between I and B, which we know is bigger because I is in A's coalition, minus the difference between I and A, right? And basically this is the stakes, right? This is how much this player I benefits from getting A's position versus B's. That's all we're saying here. And you do the same thing for coalition B. You sum it up for each people. And by the way, when you calculate, like when you would do this calculation for A, the thing about A is, we did it before, right? We had this part, the first part of it was what we did previously. We just added in minus PI minus PA. When I is A, position of A minus A is 0. So it cancels itself out. Because something minus 0 is that same something. If that makes sense, I hope. So that's what we're doing here for each player. And if we continue on to look at the math, the probability A prevails over B is equal to, all of that, right? Basically, at one level, it's essentially, this is here, right? It's also here. And then this part, B's calculation, is there, right? Same three things. But quite honestly, it looks horrible. Let's see if we can make this a little more intuitive. Okay, I am stepping beyond what Bruce does. Okay, and I'm working without a net. I'm going rogue here, and I'm going to define something called conflict resources. Because, as we were talking about, hey, let's multiply influence and salience and positions, difference in positions. What is that, right? That's a thing, right? It feels like it's a thing. If influence times salience is power, then what should we call this? And maybe Bruce did it somewhere. He has got a lot of writings on this. I'm going to call this, but I'm going to say, look, these are the conflict resources, right? The player's influence, their salience, and their distance. This is what's relevant to what they're going to do. And so for lack of a better term, I'm going to call it conflict resources because, we often talk about power resources and realism. And the conflict resources are specific to that conflict, right? And so we should probably have conflict resources of A versus B, but let's not get crazy on the notation. I'm just going to call it conflict resources with the understanding that we're looking at this case, relevant to this case, as CR sub I, right? For each player I, they have a certain conflict resource. Okay, if you go along with that, then all that stuff I did in the last site, right? All that summation I, blah, 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 blah. That's conflict resource A plus, CR sub A plus, right? And the other calculation, B's, right? Their influence, salience times the difference between one position and another, right? That's conflict resource B plus. And if we go ahead and get our, that equation that looks so horrible now, well, it looks a little less horrible, right? Because now we're saying we take the conflict resource of coalition A plus divided by this total, the sum of A plus's conflict resources and B plus's conflict resources, and we get the probability. Still pretty much the same thing we did at first. It's just been complicated by having some more stuff in there. We've added some steps. And then, of course, still the probability, well, this would be the probability that B plus prevails over A plus is going to be 1 minus that, right? 1 minus the probability of A plus over B plus. So that should make sense, right? And as always, our expected outcome, we just calculate it the same way, right, as we did before. And I'm not going to even try saying all this notation, but hopefully you get the idea. If you don't, well, let's look at an example. All right, so we got 4 players. A and B are two people fighting it out, and we have 2 other players, C and D. And the influence, if we look at influence, we have same influence as before, right, for A and B. Now we have player C, who is fairly powerful, on salience, and has an extreme position of 10, right, way down the scale from both B and A, right? We also have a player D that not very much power, little less salience than, D's got a little less salience than B, but, still some. It's still pretty, second most salient, right, of the players. And its position is very close to player A, right? So first thing we want to do is say who's in whose coalition. And, you just eyeball this, right? It should just be obvious that because player D's at a 70 and 70 is closer to 80 than it is to 40. That's the rocket science we're using here today. So D is going to be in coalition A plus, team A plus, baby. And then, coalition B plus is going to be B and C. And when I started doing this, I had D in that coalition. I heard it before I said it, so I changed it to B and C. Say it to yourself, you'll get an idea. Anyway, the point is that C is way far away, right? C's an outlier. Wants D, right? C's almost an extremist. The scale only goes from 0 to 100, but 40 is closer to 10 than 80 is. So C is going to be on B's side. So those are our 2 coalitions. Now, we want to calculate the conflict resources of each coalition. So coalition A plus has, we just do the calculations for each individual. So for player A, it's the top line, we do the calculation. And this is, this part here we did in the first example, right? We've just added 80 minus 80, which is not adding anything. It's literally subtracting 0, but we still have 200,000, right? So we still have the same number here. Now it's player D, right? Player D, we've got the influence of 50, salience of 80, and then it's the question of the difference between 70 and 40 and 70 and 80, right? So 70 and 40 is the difference between B's favorite position, D's favorite position and the opponent's position, right? So 70 minus 40 would be 30, right? 30 would be the loss if, from D's point of view, if B was to win, right? The opponent of the coalition that this is in. But if they win, they don't get 70, right? D doesn't see a 70. D gets an 80, right? If they win, they're helping A. If A wins, A is going to put in 80, right? So not quite that position, but, what's the difference here? 70 minus 80, right? So you're not at your ideal position. D will not be at its ideal position. If D could get to its ideal position, the gain would be 30. But it's going to, jump right over that position and go up to player A's ideal position of 80. So the difference between 70 and 80 is 10. So instead of a gain of 30, we now have a gain of 20, right? And so that's what we're going to get, right? Because we have 70 minus 40 is 30. 70 minus 80, absolute value is 10. 20 is the result. And so we multiply it all up and we get an 80,000. The sum of the coalition's conflict resources are 280,000. 280,000 what? I don't know. We don't have units. It's abstract. We do the same thing for coalition B plus. And, so we have the first line is B, right? And that's calculated, like I say, as before. And, we are literally subtracting 0 from it. So it's very much this mathematically same thing as before. And for player C, right, we multiply influence times salience times the difference in positions. And we're going to find that it is equal to 80 times 60. Then here's their position, right? The difference between C's position and A, right? Because A is what they're fighting against, right? So if A wins, C gets a loss of 70. But if B wins, 40 is implemented, right? So instead of 80, you get 40, but that's still, that's still 30 away, right? So what do we got? We got 70 minus, right? We've got we're preventing a loss of 70, but we still have a loss of 30. So, the gain to this is to winning for player C, in this coalition is basically 70 minus 30 is 40, right? So it's still a good number. And in fact, when you add it up, right, this player's bringing a lot to the table, right? Or as much as B. It's kind of an equal partner here. And so we see that B, same calculations before, 190. C is 192,000, sum of 382. And now with these numbers, we just plug it in, turn the crank, and we get probability calculation, right? So we take the conflict resources of A plus, it was 200,000. We divide it by the sum of 200,000 plus, 280,000 was the conflict resources of A. And we sum the two on the bottom, right? We're doing these two. It's 280 and 382, right there. And I hope that red dot's helping. I don't know. We get a probability of 42% that A is going to prevail. If the chances of A winning are 42%, the chances of B winning are 0.58, right? So having these people join in changes the fight, right? It changes, not a lot, but, from a 50-50 or 49-51, it was 51-49 in A's favor. Now it's 58-42 in B's favor, right? And the outcome is going to shift accordingly. The outcome is going to be, again, we do the calculations, multiply the probability times A of A winning times A's position, probability of B winning times B's position, right? And so we do that, A and then B, and we come up with the final answer of 56.8. Actually, not much different, right? Not that much different because we had, 60 before, and now we have basically 57. But that is how you calculate a 4-player outcome. So hope that makes sense. A little bit long video, but when you're going through these math examples, it tends to get tedious.